Okay, so this is what we did last week. Last week we sort of defined our own CNN neural network. Yeah, we just randomly add on the layers from convolution and mass pooling. We just simply stack them across and build this network. Then we train it on our cats and dogs data set. Then finally, we arrive at these findings where we found that, okay, the longer we train, the better it's the network accuracy. The network gets better, and the error of the network gets lower the longer we as much as we train. Then finally, we also take a look at how this model is trying to predict our images. We found that some of the images are misclassified. Then we found some matrices to quantify how well is this model doing, right? Then we mentioned that model which we built to classify this. Correct. So in case you work, you should come to a realization actually doesn't improve much, no matter how hard we try to modify them. And we are a very experienced people. Yeah. So that's because the feature extractor layers has is something for us to optimize. Yeah. This lecture, we mentioned those award-winning architectures. Who still remember who the four BGG, yes? ResNet, GoogleNet, yes, correct. So those developed based on trial and error, and they just happen to win the ImageNet challenge. So now those are very difficult thing to do. So we should appreciate whatever people are creating. So now today we are going to look how do we use those in our small task, which is to classify almost how to use to classify cats and dogs, differentiate between cats and dogs. And that's about today's class. So before we start the class today, I just want to give you a preview on what are we going to look at the end of this class. So today we mentioned that we want to use an established off-the-shelf architecture, CNN architecture, to perform our image classifier, right? So at the end of the day, you should see this. If we were to use a blank VGG to train the entire VGG based on the data that we have. So the data that we have is very small, right? We only have 1,000 cats, 1,000 dogs to train this model. And this VGG16 is a very huge model as we discussed. Okay. So at the end of the day, we are going to produce this output. So we will arrive at accuracy of about 65%. That is worse compared to a random network that we define. But we will also be looking at two variations of VGG16. What we will be leveraging on is the VGG16, which is pre-trained on ImageNet. So we will be looking at, we will be using the VGG model, which has been pre-trained on ImageNet in terms of their feature extraction layers. So now these feature extraction layers has been trained on ImageNet. Then what we are going to do is to remove the last layer, and we will redefine the last layer. So what is the function of this last layer? Whenever we mention this CNN architecture, there are always two components. The first component is helping us with extracting the features. And the final layer here are the layers that help us with the classification, the prediction. Okay, so now the second model here that we are trying to use is this feature extractor trained on ImageNet, but we will remove the last layer and redefine the classification layer. That means we are telling this model and say, use whatever you learn from ImageNet. Try to extract the feature from our cats and dogs image using those knowledge that you have learned. But forget about what you learned in classifying the 1000 classes. Now learn how to classify between cats and dogs. Okay, so that's what we are trying to do using the second VGG model. Okay, and the third VGG model here is something, we wanted to do something extra. We want this pre-trained model to forget what it has learned on classifying, as well as we want this model to forget a little bit about what it has learned in terms of feature extraction. This VGG16 is a very large neural network. It has a lot of feature extraction steps. So now we want to define, we want to retain the knowledge that it has learned on ImageNet for learning the low-level features. So now we want this model to then forget what it has learned at very high level. And we want this high-level feature extraction to learn the features of our cats and dogs. Okay, so we will retain the knowledge of the lower level feature extraction and retrain the higher level feature extractor in the third model that we are going to see today. So this model, so if we were to compare the accuracy of these three models, we can see that using a blank VGG model, a very complex model on our simple data set, it is going to give us a very bad accuracy compared to simple model. Yeah. But if you were to leverage on the pre-trained model, it is going to push this accuracy from 65% up to 90%. This is the effect of transfer learning. And if you were to retrain several levels in terms of feature extraction and say, learn how to extract features from cats and dogs, it is going to push the accuracy a little bit more further from 90% to 93%. Okay, so this is the effect and impact of transfer learning. And this is very important to learn nowadays. So we are covering that in this module. Okay, so for today's class, we will be looking at how to build image classifier using off-the-shelf architecture. This is a data set that we will use, the cats and dogs. And these are the 3 collab notebooks that is relevant to today's class. So on the first notebook here, it consists of the full set of code to use a randomly initialized VGG model. That means we will train the entire VGG model using our small data set. Okay, so from importing the data set, training the model, up to evaluating the performance. So the second part, the second notebook here refers to the one that we want to retrain the classifier only. Yeah. And the third part of the code, the third set of notebook is sample code for us to retrain the classifier as well as refine or fine-tune some of the high-level feature extractor. Okay. So make sure that you can access to the notebooks. Okay. So today we want to go through some of the important parts. In terms of training an image classifier, the process that we will go through is exactly the same as what we cover in week 5. Yeah. So all the steps that we cover in week 5 is summarized on the left panel here. So first of all, what we did is bringing in the image data. So in terms of bringing in the image data, what we will be doing is batch normalization as well as data augmentation, if you still remember. So after bringing in the image data, what we are trying to do is, last week, we tried to define our network. and then compiling them, train them, predict, and evaluate. So today, we will not be defining the network anymore. So this was what we did last week, right? Defining a network. And this week, we won't be doing defining network. Instead, we will be looking at how to bring in the base model, the established architecture. So after this step that is different from the previous week, we will be repeating the same task that we did, which include compiling the network, training the model, predict, and evaluate. Okay? Got it so far? Right. So let's start with batch normalization and data augmentation. So who still remember what are we supposed to do on training dataset, validation dataset, and also the testing dataset? What difference should we impose to them? Okay. No, we mentioned about data augmentation, and we mentioned that we have to treat the training images and the validation images differently. Yes, exactly. Were you paying attention or do you get the answer from the code? Either way is fine. Oh, yeah, cool. So, yeah, whatever your friend mentioned is correct. So whenever we perform data augmentation for all the images that we have, on the training images, we will have to augment the data. It means we have to apply some operations onto it. Say, for example, cropping them, tilting them, or changing the configuration so that we provide more representation of an object to our model. But on all the validation and test images, we do not need to perform all of these changes, cropping operations on them. Reason is they are used for validation. But there's one thing that we need to apply to all of the image, which is just to rescale the pixel values. Yeah. So make sure that we always start with rescaling the values of 0 to 255 into a range of 0 to 1, because our network will recognize or work best within this range of values. Okay, so this is a standard practice. So on training data set, we have to augment it using more operations. On the validation and test data set, we will just rescale the pixel values. Okay. So now let's take a look at something new today. How do we load the base model instead of defining our own network? So now we mentioned that in this class, we'll cover everything that Keras provide. So in terms of loading model, we will also be loading the base model that is available in Keras. So now what model is available in Keras? Let's take a look at this link. So once you click on that link, you will be directed to this page. So in this page, when you look at this left panel here, these are all the models which is available conveniently for you under this Keras package. Yeah. So here you can see that we have exception net, we have efficient net, we have VGG 16 and 19, we have REST net, we even have mobile net, we have inception net. Bear in mind that we don't have AlexNet because that is very basic ones. So usually people don't use them that often anymore. Bear in mind that we also don't see GoogleNet because GoogleNet is proprietary and therefore those are not publicly available. So these are all the publicly available architectures. Yeah. So now this table over here tells us how large is a model. What is the size of each model? What is the accuracy that it has achieved on ImageNet prediction? Yeah. And it will also give us a sense of how many parameters it is that will lead to how much time we need if we were to use that model to train on our data set. Okay, so this is an estimation. Question? All good? Okay. So now we mentioned that these are all the models that it has, that is available in Keras package. And how will this model exist? In what form does this model exist? So now this base model can exist in two type formats. So first type is an empty model without the pre-trained weights. The second type is model with the pre-trained weights. What are the difference between the two types? So on the first type, empty model without pre-trained weights, that means it provides you the architecture only, which is what we did last week. Last week, what we did was manually define every single layers, right? Model, add, model, add, model, add, adding the convolution and max pooling. So this empty model here consists of the exact VGG16 model as how it was published in the paper itself. That means all of this layer is predefined in these packages. What we need to do is not to call out all the single layers, but just to say VGG16 and it will bring in all the layer for us. Okay, so that is an empty model. So what is then this model with pre-trained weights? We know that these models, it will learn from data set, right? Once it learns its data set, it acquires knowledge. So when we refer to knowledge that is learned by this model, we always call this thing as weights. They are just weights, right? They are coefficients. So this model pre-trained with pre-trained weights means we use this VGG model. It has all the layers, but at the same time, every single layer here consists of the knowledge that it has learned from a particular data set. That means somebody else have used this model to train it on others bigger data set. Okay, so then it retains all the weights within here. What we can do is simply to take this and try to say that, oh, give me a prediction. Yeah. Say for example, if we were to bring in this network itself, we can just call them in, and then we provide this model an image, and this image will be able to provide us an output of what that image is about. So now what we wanted to do here is we can bring in everything, and we can also remove the classification layer. So now that model itself, those pre-trained weights, is going to consist of all the knowledge that it knows in classifying 1,000 classes of objects. But now we have a task which we are supposed to classify between cats and dogs. What we are going to do here is we remove the last layer, the classification layer, the last layer, and say we want to retrain this model to classify between cats and dogs only. So this is what we meant by model with pre-trained weights. Then what we can do with this model is then we can unfreeze the classification layers. We can also unfreeze the classification layer, at the same time fine-tune the feature extraction layers. Okay, there are two types of operation that we can do. We can bring in the entire network with its weights. We can remove the classification layer. We can also remove the classification layer and remove the feature extraction layers. Yeah. Do you get the idea what we meant by three of this? No, right? So now for unfreezing the classification layer means that this model have learned how to extract features from large data. Okay. What we are trying to do is say, hey, model, you remember what you learned from ImageNet, how you extract features. But now forget about what you learned on classifying 1,000 classes. Forget about that. I will tell you what you need to learn. So we teach the model to learn to classify cats and dogs only. That's what we are trying to do. Okay. So on the second case, we want to retrain the feature extraction layer and the classification layer, right? So now we are trying to tell this model, hey, remember how you extract the features when you learn from ImageNet. But now I want you to learn the several features from our cats and dogs. So now combine the knowledge that you learn from ImageNet to extract low-level feature, plus the knowledge that you learn on extracting the features of cats and dogs, and relearn how to classify cats and dogs. Okay, so this is going to give us better performance compared to we are training a model from scratch. Yeah. No need. Yeah, I'll show you how to do that later. Yeah. So this is how it works. Okay, so we have covered this. These are all the models that's available. So for your assignment, I do recommend you using ResNet as well as MobileNet and compare the differences. So the next step that we are going to do is to look at how do we use this function that is available in Keras. So let's go back to the document itself. So now say, for example, we wanted to try to leverage on this ResNet. So what we need to do is to click on this ResNet and we will be directed to this document. So it is important to understand how these functions work because they have been pre-coded, pre-programmed, right? There are a few things that we need to take note. So now this first line of, so now this is the code for us to call that ResNet function. Yeah. So by this code itself, we are bringing in the entire ResNet without needing to define the layer one by one. So this will give us all the layers. So now we have to define how do we want to bring in the layers. First line here says include top. What does it mean here? Include top means if let's say we say true, include top true, that means we want to import the fully connected layers. Yeah. So that means we want to import the entire thing exactly as how it is being published on the paper itself. Okay. If we say and include top equals to false, that means we just want to bring in all the feature extraction layers without importing the classification layers. So that is how we are calling the code. Another important part that we need to take note of is the weights. If we just want to bring in the architecture without the pre-trained weights, we will say weights equals to none. In the case where we want to bring in the weights or the knowledge, so then we say weights equals to ImageNet. Okay.
The model be more accurate.
Depends on how big of data set do you have. If you have a very established data set, either one may work better. It depends. So it depends on your data set and data size. Okay, so now we talk about weights. Another part to note is the input shape. There is certain requirements of how this model will work for us. So we always have to refer to the requirement of this particular model on input shape. So this is where we can get the requirements. So say input shape, it is recommended to be 224 by 224. If you still remember previously, what we have seen is we sort of set our target size to 150, 150 during the batch normalization. So this will not work for us if we want to use this pre-trained or established model. So in the case where we want to use this model, we will have to make sure that we change the target size during the batch normalization process accordingly. Okay. It is also saying that the input size shouldn't be smaller than 32 by 32. So we'll always stick with the one that is recommended here. Yeah. So another important part to take note is the classes. So these classes, the value under these classes have to be modified to suit to the classes that we are trying to predict. Say, for example, if we are trying to predict 6 classes of garbages, then these classes has to be 6. Otherwise, this model is going to assume that we have 1,000 classes in our data set. Okay. Classifier activation is always recommended to use softmax. We can also use sigmoid if we have a binary classification task, but softmax would work for all of the classes. Yeah, so this is how we should read the documentation in case we want to use a pre-trained model, in case we want to leverage on this transfer learning technique. Yeah, we can take a look at the sample code as well as the arguments to understand what each argument or parameter is about. Okay, so we have covered that, and let's take a look at how do we load this model, some sample codes. Yeah, we'll go through some sample codes. So these are all the packages that we need in the case where we want to bring in VGG16. So here, what we are trying to use is everything in Keras. We will need VGG16 model. We will also need the sequential models. If you still remember what is sequential model, there are two types: sequential, functional. So the sequential provides a template that says everything that we define after the sequential back from one layer to another layer. If you use a functional ones, that means this layer can be skipped from one to another. Okay. So this sequential model. Then we also need to import the dense neural network, the dropout, and the flatten. So remember what three of these are for? Three of this is important for us to define the classification layers. Okay. This plot model is used for plotting the graphs, and optimizers who optimizes. Yes. Yeah. So optimizers is one of them. So what does optimizer represent? It is a way for us to specify how this network should learn from our data set. Optimizers, learning rate. Okay, so now let's see how do we import an empty model without any pre-trained weights. So as what I mentioned earlier, so this is a sample code of a complete set of code. So now say we want to bring in the VGG16. So we say VGG16 in capital. So this is exactly how it is written in the packages itself. We say include top equals to true because we want the entire model. Weights equals to none. Input shape is 224 by 224. Causes is 2. Okay, so this is how we bring in the empty model without any pre-trained weights. So then we need to define another steps, which means that we want to indicate to this code and say all of this layer that we try to bring in has to be trainable. What does that mean? That means we want to train the entire model using our data set. Therefore, we have to specify that all the layers trainable equals to true. Otherwise, it will not allow this network to work on your data set. It will just say that do not update the weights. At the end of the day, you will still be getting an empty model at the end of the day. Okay. So layer equals trainable equals to true. So that's it. That's how we import the network itself. As simple as that. Any questions so far? Any idea what should happen next? Yes, question. Yeah, we'll come to that later. Yeah, so no question. So what happens after we define the network? Yes, compile. Yeah, compile means we have to define what error matrix should this network use whenever it trains. And we also have to define the optimizers, which is how this network should learn from our data, how fast it should learn. Should it take a stepwise approach or should it take a jump approach? Okay. So we'll come to that later. But before we come to this compilation, I just want to cover on how do we bring in the model with pre-trained weights. So in order to bring in the model with the pre-trained weights, by just unfreezing the classification layer, so we are going to take a look at the second condition here. So we are going to bring in the VGG16 like what we did before, but this time round we'll say include top equals to false. So we are chopping off the head or the classifiers. At the same time, we want to bring in the weights. That means we chop off the head, but bring in the weights for all the rest of the layers, the feature extraction layers. Yeah. So for the feature extraction layer, we bring in the layers plus weights. So here weights equals to ImageNet. Input shape is 224 by 224. Then that's it. Yeah, this is on defining the network or the architecture that we want. So then we have to mention to this network to say that, okay, layer trainable equals to false. What does that mean? And why false?
Does not, the data set does not need to.
Yes, correct. So what we are trying to say to this network is that, okay, so now retain whatever you learn. Do not need to update the weights based on the cats and dogs images. Yeah, so we'll just leverage on all the knowledge that it has learned. So trainable equals to false. So then, okay, so that's it. And what do we need to do is, because we have already chopped off the top, the head, we don't have a classifier. So now we have to define the classifier. In this case, in this sample code, what I'm trying to do is to attach a dense neural network, a fully connected neural network to do the classification task. So how do we do that? It's very simple. The process is similar to what we have seen last week, where we will start off with defining the sequential model. Okay. So the first layer to include in this process is say, it is a sequential model. So now, once we say that it is a sequential model, how do we bring in the entire VGG16 architecture is then to say VGG transfer learning dot add VGG16, this one. So by saying this VGG16, we are basically bringing in all of the layers in VGG16 from the previous code here. Okay, so now, what happens between feature extraction and classification? Yes. So at the end of feature extraction, we are producing a feature map which is in 2D format. So before we channel this feature map into our fully connected layers, we need to flatten them into a 1D array. And therefore, the layer that exists between the feature extractor and the classifier should be the flattening layer. Okay, so we add on the first layer, which is flattening. After flattening, we know that all the layers is related to classification. Yeah. So then we go about and add on more and more layers that help us with classification, learning the features to produce a prediction. Yeah. So this drop off means that we want this network to drop off some of the neuron for efficiency. And these dense neural network are the network which is trying to learn the features that we have extracted. So in this case, we are just defining a very small neural network towards the end, which consists of one layer that have 512 neurons. And after this one layer, it is supposed to give us the output. So bear in mind that in the output layer, we should always define the number of neurons that is relevant to the classes which we are trying to predict. Say, for example, we have cats and dogs, that's 2 classes, and therefore the final layer here consists of 2 neurons. Okay, activation function for the classification step have to be softmax. Okay, and the activation function for all the rest of the layers is recommended to be ReLU. Okay, that's it. That's how we define a model with pre-trained weights and unfreezing the classification layers. Any question? No question. So if there's no question, we are going to move on to the third one, which is the one relevant to the question which our friend have asked. So how then do we chop off the classification layer and also relax some of the feature extraction layer? So what we are trying to say here is we want this model to retain the low-level feature extraction layers, but we want these top layers to learn from our cats and dogs images. Extract the features from our cats and dogs image. Okay, so these are called high-level images. So what we are going to do is similar to what we have just seen. VGG16 include top equals to false. So then we will chop off the head. Then we will want to bring in all the weights that has been trained on ImageNet. Input shape is as what it is specified. Okay. So now we want to say that all the layers trainable equals to true, and then we will reset the layers that we want to train. Yeah. So in this case, we will need an additional steps to tell this code and say which layer in the VGG feature extractor do we want to retrain. So in that case, we will reset the trainable equals to false. So for all the layers in the VGG model that we define, we want to relax certain layer. So now, in order to direct the relaxing of this few layers, we need to know the name of the layers. Yeah. So now, how do we know the name of the layers? Last week, we covered the code called .summary, right? So once we use this .summary, we will be able to call out the name of every single layers. Name of every single layer. And say, for example, once we get the name, we will be able to direct these layers to be unfreeze. So then we will have to say which layer do we want to unfreeze. Say block 4 and also block 5. So we say block 4 and block 5, set trainable equals to true. That means we will retrain these blocks. And for the other layers, other than block 4 and block 5, we will not train them. Layer trainable equals to false. Yeah. So once we define this trainable true and false, we will have to make sure that we are defining the correct layers to be trainable and correct layers to be not trainable. So this is a code for us to take a look at whether we are defining them correctly. So once we use that code, run that code, it will provide us an overview of what are the blocks we have in VGG16. And we know that these layers are not trainable. And this block 4 and block 5 became trainable because we have defined it to be trainable. Yeah. As simple as that. Any question? No question. So the next step here is exactly the same as what we have done in the previous step, which is defining the classifiers. Yeah, because what we are trying to do here is relaxing some feature extraction layer and also retrain our classification model. Okay. So in the demonstration code that I provide, I'm using the exact same classifier. Okay, so that our model performance is comparable. Yeah. So once we load the base model, we can do a few things. For example, we can visualize how our network look like. There are two ways of visualizing our network. First one is to use the .summary, where it gives us a tabular format of preview. So from this summary table, we are able to get all the numbers of parameters that we are trying to learn from this network. So we can also use this plot model to give us a graphical representation of the entire network. So this is how the entire VGG16 look like. It is very straight and linear. In the case where you visualize a ResNet, it will be very beautiful. Okay. Okay, so yeah, we have just done how do we load the model